The screen is nearly black. Then a thin band of starlight appears, clean, pale, almost fragile. A spectrum, a barcode made of light, and inside it, a small notch sharp enough to feel like a confession. Sodium, not on Earth, not in a lab. In the atmosphere of an exoplanet so far away, its light arrives as leftovers photons that have been filtered through a rim of gas during a transit. We can see that filtering as a tiny wavelength-specific change in the star's light. And when we stack those changes into a transmission spectrum, sodium can show up as a distinctive feature. But tonight on this plot, it doesn't sit still. Across 10 transits, the sodium line on HD 209458b appears to shift. It doesn't just wobble in the noise and settle back down. It drifted again. That phrase matters because it doesn't promise a discovery. It promises a test, signal versus artifact, an exoplanet atmosphere speaking, or a measurement being fooled. This is what we're really watching, a tiny feature moving by a tiny amount over and over through 10 separate passes of a planet across its star. Token by token, the title makes a claim and dares us to challenge it. Sodium line on HD 209458b drifted again, retrieval bias across 10 transits. The target is named, the method is embedded. And the clue is not just sodium, it's sodium behaving strangely across time. So what does it mean for a line to drift? One's meaning is almost romantic. The atmosphere itself is changing. Winds, temperature layers shifting the effective altitude where sodium absorbs. A planet-scale weather system rewriting a signature we thought would be stable. Scape. If that were true, it would be a rare kind of intimacy, seeing dynamics in an exoplanet atmosphere, not as a theory, but as a pattern in the data. But the more honest meaning, the first meaning we owe ourselves, is harsher. In exoplanet spectroscopy, the planet is never alone in the experiment. The star is the light source, the instrument is the translator, and our analysis, the retrieval, is the judge. A drift can come from the world, or from the way we build the world out of faint starlight. That's the paradox the title hands us. We measure more carefully, across more transits, and the answer seems to move anyway. 10 transits should steady the story, and yet the sodium line drifted again. Here is the simplest picture. A transit happens. The planet slides across the star. For a short time, some of the starlight passes through the outer edge of the planet's atmosphere before reaching us. If the atmosphere absorbs certain wavelengths, sodium's in this case, the planet looks ever so slightly larger at those wavelengths. Not by much, just enough to carve a notch in the spectrum. We repeat that 10 times, 10 opportunities to confirm the same notch, and then the notch appears to shift. The evidence moment is right there on the screen. Stacked spectra, 10 separate transits, each with the sodium feature in nearly the same place, except not quite. Some sit a hair to one side, some deepen, some soften. The pattern looks like motion. It looks like behavior. It looks like a line that won't settle. But in this field, looks like it's where false positives begin. Because a spectral line can move without the planet doing anything at all. Instrument systematics can do it. A subtle wavelength calibration drift the instrument's internal ruler, sliding by a fraction can shift where the notch appears. Thermal stability matters. Detectors have their own moods. Wavelength solutions can creep. Even if the sodium absorption is real, the measured center can wander if the calibration wanders with it. This is signal versus artifact, in its purest form the same notch, but nudged by the translator. And the star can do it too. Even if the planet's atmosphere is steady, the star's surface is not always uniform. Spots in brighter regions, faculae alter the star's own line shapes and colors. In transit, we are subtracting star alone from star with planet. If the star changes, or if the planet blocks a different patch of the stellar surface from one transit to the next, that subtraction can imprint a counterfeit drift. The line moves and we blame the planet when the contamination lived on the star all along. That's not a minor detail. That's the difference between an atmosphere changing and an experiment misbehaving. So the key question of this opening chapter isn't, is there sodium? That's too easy, too comforting. The real key question is, what does it mean to trust a drifting spectral clue in an exoplanet atmosphere, especially when the drift repeats again across 10 transits? We know the case is plausible. HD 209458b is a benchmark exoplanet for atmospheric studies. Sodium has been part of its story. We know the method is legitimate. Transit spectroscopy can, in principle, isolate atmospheric fingerprints. And we know the discomfort is legitimate. Measurements can vary from transit to transit for reasons that have nothing to do with the planet's chemistry. So we stand at the first fork in the narrative. One path says, the drift is telling us something true about the exoplanet atmosphere, about structure motion, or where sodium lives in the layers of gas, spec. The other path says the drift is telling us something true about us, about instrument systematic stellar activity, and the quiet ways our own assumptions can sculpt the result. Either way, the title has already made its promise. This is not a triumphal detection story. It's a credibility story. The case of a line that drifted again, and what it takes to decide whether it's the planet speaking or the measurement being fooled. To answer that, we have to go into the machinery. Not the hardware, not the glamour, just the chain of inference that turns starlight into an atmosphere, and an atmosphere into a claim. We have to name the step where retrieval bias can enter, and why 10 transits can still leave us unsure. So we turn from the moving notch back to the pipeline that gave it meaning, and ask carefully how an exoplanet atmosphere is built from light, and how easily that construction can shift. The starlight returns again and again, like a witness we keep bringing back to the stand. 10 transits, 10 moments when HD 209458b passes in front of its star and the star's light thins by a hair. And each time we take what we can, get a spectrum that is never clean, never generous, never built for us. It arrives with scars, noise, drift, variability, and we ask it to testify anyway. Here is the heart of how we know and why the title's warning matters: retrieval bias across 10 transits. The sodium line didn't just appear, it didn't just change, it drifted again, and we only know that because we process the light through a chain of choices. Those choices are not corruption, they're necessity. But they can become a false positive if we forget they exist. So what are we actually doing when we say we retrieved an atmosphere? We begin with something brutally simple, a time series of starlight during a transit. The planet blocks a fraction of the star. At some wavelengths, it blocks a tiny bit more because the planet's atmosphere is more opaque there. That wavelength-dependent difference is the raw clue, not a picture of clouds, not a chemistry set in space, a difference, a subtraction. And subtraction is where mistakes learn to hide. We take spectra before, during, and after the transit. We correct for known instrumental behavior. We align wavelengths so that sodium is always measured at the same place on our scale. We normalize brightness changes so that what's left is truly about wavelengths, not just overall dimming. At each step, we are calibrating the experiment, making a decision about what counts as the star, what counts as the planet's atmosphere, and what is merely the instrument itself. That's the first evidence moment in this section. The pipeline exists because the planet's signal is smaller than the mess around it. The pipeline is not optional. It is the observation. Then we build the transmission spectrum, how deep the transit appears as a function of wavelength. This is where the sodium notch becomes visible, at all an imprint in the star spectrum created as light grazes the exoplanet atmosphere. But seeing a notch is not the same as knowing what it means. That's where retrieval enters. A retrieval is a disciplined kind of inversion. We have data, our measured spectrum. We have a forward model physics that predicts what the spectrum should look like for a given atmosphere. And we search through a range of atmospheres to find which ones best reproduce the data. It's not a single answer. It's a family of answers, each with a probability. The output isn't a proclamation. It's a set of constraints. And those constraints depend on assumptions. Model assumptions that the data alone cannot fully determine. This is where bias can be born, without anyone intending it. For example, we often treat an atmosphere as one-dimensional, a single vertical column that represents the planet's limb everywhere. But a real exoplanet atmosphere is three-dimensional, with day-to-night gradients, winds, and changing temperature structures across the limb. If the planet's terminator is not uniform, a 1D retrieval can explain complex reality by shifting simpler parameters, sometimes by moving where a line appears to center, or how broad it must be to fit inconsistent transits. We also make choices about temperature profiles, about whether chemistry is in equilibrium, about how metallicity might vary, about whether there are clouds or hazes, and how they scatter light. These are not frivolous choices. They're the minimum scaffolding needed to interpret a spectrum at all, but scaffolding can become a cage. Now return to the title's clue, the sodium line drifted again across 10 transits. There are at least 2 ways retrieval bias can make that happen. One is blunt. The retrieval is asked to fit 10 slightly inconsistent data sets, and it compromises by shifting the line position rather than admitting that the data sets are not directly comparable. The drift becomes the model's way of reconciling disagreement. The second is subtler priors. A retrieval cannot search every possible atmosphere equally. It needs prior ranges, reasonable boundaries on parameters. If those priors push solutions towards certain temperature structures or composition regimes, the fit may prefer a slightly shifted sodium feature as the path of least resistance. The line moved because the prior gave it room to move, and the model found that motion cheaper than other explanations. You can feel the tension sharpen here, detection versus interpretation. We might agree there is absorption in the sodium region, but the claim that it drifted is interpretive. It lives downstream of calibration and model assumptions, and 10 transits, which sound like an antidote to uncertainty, can actually amplify this. Because with more transits, we are tempted to combine them, stack them, force them into a single narrative. If there is hidden transit-to-transit variability from the star, or hidden calibration drift from the instrument, the combined dataset can look impressively precise while being precisely wrong. That brings us to the required confounder test in this How We Know section 1. The outline demands we name clearly retrieval priors / model assumptions. So we say it plainly. Retrieval bias can manufacture coherence. It can take a spectrum that is almost the same 10 times and produce a story of a sodium line that drifted again, even if the underlying atmosphere was stable and the differences came from somewhere else. That's not a failure of retrieval. It's a warning about how powerful retrieval is and how careful we have to be when a result looks like behavior. This is where the episode's credibility framing tightens. The title doesn't say sodium discovered. It says drifted again. It says retrieval bias. It says across 10 transits. It is quietly telling the viewer the drama is not the element. The drama is whether our inference chain is lying to us. And now we're ready for the next move. Because if retrieval bias can shape a drift, Something else can create the inconsistencies the retrieval is trying to explain. Something upstream. Something we often treat as background. The star. We have to change perspective. We have to stop thinking of the star as a backlight and admit it as an active participant, one that can sculpt the transmission spectrum through contamination and stellar activity. If the star's surface is uneven, the planet can appear to carry an atmosphere it doesn't have, or to change an atmosphere that never changed. So we step away from the retrieval outputs and look back at the light source itself. Because the star is not a lamp. The star is part of the experiment. A star fills the frame, not as a point, as a surface. It looks calm at first, an even glowing disk. But then the light shifts and you can see what the equations always knew was there: texture, subtle modeling, regions that are slightly darker, regions that are slightly brighter, a face that changes with time, and suddenly, the exoplanet feels less like the main character and more like a small moving mask crossing a complicated stage. This is the perspective shift the outline demands. The star is part of the experiment, because when we do transit spectroscopy, we are not measuring a planet in isolation. We are measuring the difference between two versions of starlight that has passed through an exoplanet atmosphere and starlight that has not. If the star is not uniform, that difference can lie. So we return to the title's tension, and we say it clearly. The sodium line on HD 209458b drifted again across 10 transits. But what if the drift isn't the planet? What if it's the star moving beneath our subtraction? This is not a niche technicality. It is one of the most potent false positives in exoplanet atmosphere work stellar contamination. Picture the stellar surface as a quilt. There are cooler spots. There are brighter faculae. They do not share the same spectrum. Their absorption lines are shaped differently. Their colors differ. If some of those regions are not covered by the planet during transit unocculted spots or faculae, then the out-of-transit spectrum and in-transit spectrum are not directly comparable. The planet is not just blocking light. It is changing which mix of stellar surfaces contributes to the light we receive. That can mimic an atmosphere, and it can mimic an atmosphere changing. Here's the evidence moment, the one we can point to without inventing numbers. If the star's line shapes change with activity or rotation, then the apparent transmission signal around sodium can shift even if the exoplanet atmosphere is stable. The notch looks like it moved because the baseline moved. It's easy to miss because the logic is emotionally backwards. We want to blame the faraway world. It feels more cinematic. But the nearer object, the star, has more leverage over the measurement. So we ask the key question of this section: could the sodium drift come from stellar contamination rather than HD 209458b's atmosphere? A star rotates. Active regions evolve. Over the span of 10 transits, the planet may cross different chords of the stellar disk, higher latitude one time, closer to the equator another. Even small differences in which parts of the star are blocked can matter if the star is heterogeneous. If the stellar surface is uneven, then the planet becomes a scanner, sampling different stellar spectra in different nights. That's the tension pair in plain language: planet atmosphere versus star contamination. Now the caution: we must not overstate what the outline didn't claim. We do not have in the source of truth outline a specific measured correlation between the drift and a stellar activity indicator. So we stay honest. We keep it conditional. If the drift aligns with signs of stellar activity, if it tracks changes in the star's behavior rather than the planet's orbit, then the star becomes a leading suspect. If it does not, the case shifts back toward instrumentation, retrieval assumptions, or real atmospheric variability. But even without that correlation in hand, the principle stands: stellar heterogeneity can produce wavelength-dependent biases in transmission spectra, and those biases can masquerade as both the presence of atmospheric absorption and changes in that absorption from transit to transit. Now bring sodium back into view. Sodium is not just a label, it's a part of a spectral line landscape. The star has sodium features of its own. If spots and faculae alter stellar line profiles, then the region of the spectrum where we hunt for sodium absorption is exactly where stellar contamination can do the most damage. The exoplanet atmosphere signal is entangled with the star's own chemistry and surface physics, which means the title's phrase, "drifted again," takes on a darker edge. It may describe not a planet's weather, but a measurement struggling with a living light source. And this matters far beyond a hot Jupiter, because the search for signs of life, biosignatures, and any discussion of technosignatures tied to exoplanet observations must pass through the same gauntlet. If stellar contamination can shift a sodium line, it can also distort subtler molecular features that people might someday be tempted to interpret as life. The discipline we practice here becomes a discipline we will need later, when the stakes feel higher and the signals are weaker. But we're not leaping there yet. We stay with the case. We take the star seriously as a confounder. We admit it as a participant, and then we ask if the star can fake a drift, what else can? Because there is another kind of dishonesty in the system, one that doesn't come from biology or stellar magnetism, but from machinery and math. Instrument systematics can shift a line. Calibration drift can slide the wavelength ruler. Clouds and hazes can reshape a spectrum until the retrieval tries to explain what's left by moving parameters around. And line lists are catalogs of how atoms and molecules absorb can be incomplete enough that we misattribute or misfit what we see. So the change of perspective completes its work. We stop staring at the planet alone. We widen the frame to include the star, and we prepare for the hardest accounting, the limitations that can turn a drift into a mirror. If we want a best current conclusion, one we can say without flinching, we have to run the sodium drift through the full set of suspects: instrument systematics, cloud/hazes degeneracy, and the assumptions embedded in our models. So we move into the limitation-heavy chapter, where the goal isn't to win the mystery. The goal is to not be fooled. The spectrum returns, but now it's overlaid with something colder than curiosity. A checklist, not a list of triumphs, a list of ways we can be wrong. Because if the sodium line on HD 209458b drifted again across 10 transits, then the burden is not to explain it with the most cinematic story. The burden is to see whether the drift survives. Contact with everything we know can counterfeit it. This is the limitation-heavy section, the part of the episode that refuses to look away. We start with the most ordinary villain in observational science, the ruler. A wavelength scale is a promise. It says this pixel corresponds to this wavelength, this dip corresponds to sodium, and sodium is right here. But that promise can slide. Wavelength calibration drift can nudge the entire spectrum or distort it subtly from one observation to the next. Thermal stability matters. Detectors have quirks. A pipeline can align spectra in ways that inadvertently pull a line to a new center. So here's the tension pair stated plainly: model fit versus calibration drift. And here's the evidence moment we can stand on without inventing numbers. If the instrument's internal calibration changes between transits, or if the way we correct and align the data changes, then a stable atmospheric feature can appear to move. The sodium line becomes a reflection of the instrument's stability, not the exoplanet atmosphere's behavior. Now we take the second suspect, the atmosphere itself, not as truth, but as camouflage. Clouds and hazes are not decorations. In exoplanet spectroscopy, they are a degeneracy engine. They can flatten, mute, and reshape features so that the spectrum loses contrast. When that happens, retrieval models have less to grab onto. They compensate. They trade one parameter for another. They can push online depth broadened shapes, or prefer solutions that shift a feature slightly because the model is trying to fit a muted ambiguous signal. This is the tension pair detection versus interpretation. The sodium region might still show absorption, but the feature's apparent center and strength can become entangled with assumptions about scattering altitude and temperature structure at the limb. That's not because the planet is playing games. It's because the data are thin and the models must choose. And now the third suspect, the library we consult when we see a dip in light. We call it a sodium line because sodium is a known absorber and because the feature resembles what sodium should do. But our interpretation depends on line list reference data that tell us where lines should be and how they behave under different conditions. If those references are incomplete, or if we misidentify what we're seeing, the retrieval can still produce a fit that looks convincing while being subtly wrong. This is the tension pair signal versus misidentification. It's not the most likely explanation in every case, but it belongs on the board because the title's claim is about a specific measurable clue, a line that seems to drift. The more specific the claim, the more specific the failure modes. Now we bring the suspects together because this is where limitation heavy means something not one confounder at a time, but confounders that can cooperate. A small calibration drift can shift the line a little. Stellar contamination can change the baseline a little. Hazes can mute the feature a little. Retrieval priors can help by selecting the cleanest looking narrative across 10 transits. None of these has to be dramatic. Together they can create a drift story that feels consistent enough to repeat drifted again, even if the exoplanet atmosphere never changed. So what can we say that is defensible? We stay anchored to what the outline allows. We don't invent a definitive correlation. We don't declare a solved case. We state the best current conclusion, and we keep the honesty tags visible. The sodium absorption is likely real in the sense that there is an absorption feature associated with the transmission signal. Sodium has historically been part of the atmospheric story for this benchmark exoplanet. And the repeated observations across transits strengthen the case that we are not looking at pure noise, but the drift the behavior over time is where the ground softens. With 10 transits, a persistent pattern is more suggestive than a one-off. It's tempting to treat persistence as proof, yet persistence is not immunity. A stable, systematic repeated 10 times can look like a stable trend. A repeated reduction choice can reproduce the same bias. A stellar surface pattern can reassert itself over the cadence of observations, so we land where the outline lands. Best current conclusion. The sodium feature exists, but the reported drifted again is plausibly dominated by a mix of retrieval bias, stellar contamination, and instrument systematics, unless independent cross-checks can show that the shift tracks a physical change in the planet rather than the star or the calibration. That sentence matters because it is the discipline of the series. In miniature, we do not downgrade the data. We do not inflate the interpretation. We acknowledge what we can claim and we name the confounders that could mislead us. Now we make the credibility framing explicit because the title itself is doing the ethical work. It doesn't sell sodium as a trophy. It sells the uncertainty as the point. The case of HD 209458b, the case of transit spectroscopy, the case of a sodium line that drifted again across 10 transits. This is what exoplanet atmosphere science actually looks like when it's honest. Not a single clean answer, but a set of competing explanations, each constrained by what we can measure and haunted by what can contaminate. And the point is not to end with doubt for its own sake. The point is to see what this doubt teaches us about the next harder questions. Because sodium is comparatively forgiving. It's a strong, familiar signature. If even sodium can appear to drift, then the path from a faint spectral feature to signs of life becomes narrow and steep. Biosignatures must survive the same confounders, stellar activity instruments, systematics model assumptions, without collapsing into false positives. This is where we step out of the detective story and into the meaning of the method without pretending we've left the science. We treat uncertainty as part of the measurement, not a flaw to hide. And we prepare the final turn, not to announce life, not to announce defeat, but to ask what kind of thinking this field demands when the evidence is always partial and the temptation to overinterpret is always waiting. So we carry one last question forward quietly into the cosmic checkpoint. If we can be fooled by drift in a sodium line, what will it take to not be fooled when the molecules are rarer, the claims are heavier, and the word biosignature enters the room? We leave the checklist on screen for a moment longer. Then we fade back to the thin ring of starlight during transit, because that is all we ever truly get, and we move into the ethics of a faint signal. The planet crosses again, not in triumph, in silhouette, a small, perfect bite taken from a star. Around that dark curve, a thin rim of light starlight that has grazed an exoplanet atmosphere before reaching us. The kind of light you can miss if you blink. The kind of light that can carry a biosignature someday, or carry a lie. The sodium line hangs in memory like an afterimage, a notch in a spectrum that seemed to shift, a feature that drifted again across 10 transits on HD 209458b. And now, at the edge of this story, the title reads less like a headline and more like a warning label: Retrieval bias across 10 transits. Because this is what exoplanet science really bargains with. Not certainty, not direct contact, but inference, and the responsibility to name what could mislead us before we name what we hope to find. This final section is a checkpoint, not an ending. A place to ask, what does it mean to chase signs of life biosignatures in atmospheres we cannot touch, using measurements that can be bent by contamination, instrument systematics, and model assumptions? The answer begins with humility but not surrender. Biosignature claims any claim that a gas mixture or spectral pattern points toward life must be built on the same foundation as sodium: repeatable observation, careful calibration, and retrieval that admits uncertainty rather than hiding it. The greatest danger isn't that we won't see something, it's that we'll see it and misread it. So we take the sodium drift and treat it as a rehearsal. Sodium is not life. Sodium is a training weight. And it taught us something brutal. A signal can be real, and its behavior can still be ambiguous. The feature can exist, and the drift can still be a false positive, stitched together from stellar heterogeneity, calibration, drift, and retrieval bias. That is the tension pair for this closing biosignature claim versus false positives. Because the future headlines, we can imagine oxygen, methane, strange combinations would arrive the same way sodium did, as tiny changes in starlight interpreted through models. If we can be fooled about motion in a sodium line, then we can be fooled about meaning in subtler molecules. This is not cynicism. It's the minimum honesty required by the data, and if we allow technosignatures into the frame at all, we do it carefully tied to observation channels and tagged to speculation. Some technosignature ideas involve atmospheric industrial gases or unusual spectral features that could in principle be sought through spectroscopy. But they would be even more vulnerable to false positives because the features would be faint, the assumptions heavy, and the confounders relentless. So the lesson is not don't look. The lesson is know what looking costs. The cost is that you must treat the star as part of the experiment. You must treat the instrument as part of the story. You must treat retrieval not as an oracle, but as a constrained interpretation that can be nudged by priors and simplifications. And you must be willing to say open where the data do not yet close the case. Now a second evidence moment this time, not a measurement, but a discipline. What increases confidence is redundancy, multiple wavelengths, multiple epochs, and ideally confirmation across independent instruments or reduction pipelines. Not because it eliminates uncertainty, but because it exposes whether the story is tied to the planet or tied to the measurement. If the same atmospheric conclusion holds under different assumptions and different data paths, it hardens from suggestion into constraint. And this is where the titles across 10 transits turns into a quiet moral repetition is necessary but not sufficient. 10 transits can reveal a pattern. 10 transits can also reproduce the same bias 10 times. So we name the final unknown exactly as the outline demands measurable, specific, and resolvable in principle. Here it is. The named unknown is stellar heterogeneity versus sodium line drift amplitude. Not uncertainty in general, not more data as a vague wish. A concrete question: how much of the apparent drift is driven by the star's changing surface spot's faculae activity versus how much is truly a change in the exoplanet atmosphere, and what would resolve it in the language of measurement? More transits, yes, but with simultaneous monitoring of stellar activity and broader spectral context that can separate stellar contamination from planetary absorption. Cross-checks that can test whether the drift tracks the star, the instrument, or the planet. The goal is not to win an argument. The goal is to identify the source of motion. Now the camera returns to the visual anchor that began this episode, the stacked spectra. 10 faint barcodes of light, 10 sodium notches. A line that seemed to slide just a little left-right, uncertain in its own identity. The human mind wants to turn it into a message, but the honest mind treats it first as a measurement under stress. And in that restraint, something profound emerges. Because this is what it means to listen for signs of life across interstellar distance. It means accepting that the universe speaks softly and our instruments translate imperfectly. It means that the clearest achievement is not a claim we can't defend, but a question we can measure our way toward. Two closing images remain both quiet, both faithful to the title. One, the sodium notch hovering over the 10 spectra as the labels fade, leaving only the line, and its error bars proof and doubt in the same frame. 2, the silhouette of HD 209458b in transit, the star's rim luminous, the atmospheric ring barely there, an exoplanet atmosphere reduced to a thin edge of starlight, and the last sentences spoken low without celebration. In the end, the line doesn't just measure a world, it measures our discipline. If sodium can drift again, we learn to ask, is the cosmos changing? Or is our interpretation finally catching up? We hold on that thin rim of light, not because it answers us, because it keeps the question honest.